So a more complex example, in hyperelasticity, you define this strain energy function that is nonlinear and depends on the displacement, and you want to minimize the total energy of the system. So this is a functional that we want to minimize, and the implementation of this system is basically mirrors the mathematics, and the linearization is just the same, automatic. So here's a nice color picture. This is a simple hyperelastic material, which is just twisted. It's a box, and you can perhaps see that these lines, they're not, well, it's not linear. With linear elasticity, you would just get straight lines. So, how much time do you have? I'm basically done.
You can have some more minutes.
A few more minutes?
Yeah.
Okay. So I only have 30 more slides or something. Expressions are represented internally as expression trees. So consider this simple expression, and you can decompose this into a sequence of terminals and elementary operations. So the terminals are functions and int value objects, and then we have a sum, which is represented by a sum object, and well, the same here, and then we have a product of the sum objects. So the representation of this expression will include two function instances, two int value instances, two sum instances, and a product. And visualized as a tree, it looks like this. So you can actually get, there are scripts that let you see the expressions in this way, using the dot graph language. And I think I'll just skip this. So automatic differentiation basically means, yeah, I'm not going into that detail. There's one thing you need to think about when working with UFL. It's based on tensor algebra and index notation. So there's a difference between the identity matrix, which is a tensor expression with a shape 3 by 3, and the Kronecker delta, which is a scalar valued expression with 3 indices I and j. And when working on paper, you usually switch seamlessly between these without really thinking about it. In UFL, you need to do this mapping manually. So you need to, if you have an index expression and want to work with a tensor, you need to actually do the mapping. So going from a tensor to a scalar valued expression is done by indexing. And you can make slices, take the row vector and the column vector. And going the other way is done by the functions as vector or as tensor. So you can look up the details in the manual. And this is the class hierarchy for all the expression types in UFL. And I have scripts so you can get subtrees and see these all these trees if you need to, if you want to get an overview of the structure of the code. So, okay, I'm done now. Let's discuss this how to extend UFL afterwards. What we need, but we need to define what extends means, because in the end, if we want UFL to be fully extendable in any way, then we're making a full programming language, and that's not what we're doing. That's a quite different project. But we can perhaps define some hooks where you can attach some kinds of features for experimentation. I don't know. Many things are easy to add to UFL, but the complication is in Dolphin and the foreign compilers. Okay? I guess we'll take questions mostly after the talks. I'll be around.